this week's Embedded Insiders, Brandon and Rich tried to decide if datasheet specs are reliable, or if industry benchmarks are the only reasonably accurate measure of component performance without actually testing them yourself. Later, NVIDIA CEO Jensen Huang discusses how the company's pending acquisition of ARM is progressing, and what benefits the combined company will bring to each other and the market as a whole if the deal passes regulatory checks. Jensen also weighs in on the semiconductor shortage and how his company plans to keep pricing in check amidst supply and demand volatility. Finally, Tiera Oliver investigates the world of voice processing at the edge, where companies are adding more AI, but not necessarily more processing. Engineers from Knowles Intelligent Audio and Cadence Design Systems weigh in on how classical DSP is being used to make your smart virtual assistant as clever as possible at battery scale power consumption. And to bring things full circle, Tiera introduces MLPerf Tiny Inferencing benchmark that can help voice recognition designers determine how fast, accurate, and low power their edge AI stacks can be before building out complete systems.
Hello and welcome to the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and I'm here with Rich Nass, who's the EVP of Embedded at Embedded Computing Design and Open Systems Media. How you doing, Rich?
I'm doing okay. I picked up a cold over the weekend, but as my wife said, just get over it.
Man flu.
Exactly. So I'm soldiering on.
Right. I've never had according to all of my partners throughout the years, I've never actually had the flu. I've always just had the man flu, and I had needed to get over it.
Okay. I'm not sure what that means exactly, but okay.
So, what's going on at the smart home of Rich Nass?
Well, I don't know if I've related the story, so I'll tell you the story about my smart television, which, you certainly have to air quotes around the smart when you talk about a smart television. But I'm out there, I guess this was about 3 weeks ago now, watching the Mets. And this is my outside TV. And I'm in Florida where the humidity can be brutal on an outside TV. But I'm watching the Mets, and all of a sudden the screen goes black. So first thing you do is you hop on the Best Buy app. You're like, all right, how much is this going to cost me for a new TV? So I start shopping around actually, before I did that, I did all the usual stuff. Make sure the power was there and blah, 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 and all that stuff. Seemed to be that the TV was dead. So I chopped around a little bit for a TV. And then I happened to be on the phone with my brother the next day, telling him the story. And he says, "You're an engineer, fix it." And I said, that never even crossed my mind to fix the TV. Okay. So here I am with my TV, and my wife and I up on the counter outside. We got the TV down, and I put it on the table over a blanket, and I took the back off, and here I am with my multimeter, and I figured out that it was not outputting power. There's basically two boards. There's a high power board and a low power board. The high power board was not outputting any power to the low power board. So I went on eBay and found that exact board to my TV. Bear in mind, the TV is about 3 years old, and it's a high-end TV. I found the same board on eBay for $65. I said it's worth a $65 risk if that's not what it is. Ordered the board. A week later, the board arrived. Popped the new board in. Bang! I'm watching the Mets again. Life is good.
Wow! Look at you. They said that you'd been off in the media game way too long, but they were wrong.
See, 8 years of college finally came in handy.
Right.
No, Mom, I'm just kidding. It's not 8 years of college, I swear.
What do you think it was? You think it's just a blown capacitor or something?
That's exactly what it was. Yep. And I mean, if I really want to get into it, I could have replaced the capacitor probably for a couple of bucks, but this was pretty easy to do once I zeroed in on the problem.
Man, those capacitors, I've had a few mid to low end electronics over the past couple of months go dead on me, and it's the capacitors always. So we need our friends over in the analog and power segment to step their game up, it sounds like.
Well, especially if you're going to be watching the TV in 100% humidity.
Yes, for sure. Or maybe 115-degree weather like we have here. But
this is true.
Anyway, speaking of that, how would you be able to tell from a data sheet if a capacitor or something like it would be able to stand up to your 100% humidity or 115-degree weather?
Well, there are ratings like that where they are rated for humidity and altitude, but for a consumer device, you're not going to see that. And I actually just read that they are making televisions for that use, but you're going to pay big bucks. It's just not worth it. Most consumer devices have become disposable, and your average consumer would have thrown the TV away,
right,
and bought a new one. But no, I don't think that you're going to find that stuff on your average Joe data sheet.
Well, what if you're an engineer and you're trying to figure out whether or not you want to use a processor or an operating system or whatever, or if you're going to have to throw it away in a couple of years, then what do you do? Just trust the data sheet?
Yeah, I think so. The data sheets, I don't think people lie about data sheets. They misconstrue the information, if I'm saying that right, where, to make it look like under certain conditions it works. But under those conditions, the information's accurate, in my opinion.
Yeah, I don't think it's inaccurate. I think that what more often is the case is that the data sheet shows you some incredibly hypothetical lab generated scenario where, if everything is perfect and, you do the hokey pokey, then this component, software or hardware, will perform this way. And in reality, that's just not, it's not reality, right?
Yeah, you're making me think of the miles per gallon specs that
right
that they put on cars.
Right. My Chrysler never once has gotten 35 miles to the gallon, not even in the first 3 weeks I drove it.
Well, you got to park it on the top of the mountain.
Right. So if you're an engineer or whatever, obviously one of the ways that the industry over time has tried to combat this is through the use of benchmarks. And we've had benchmarks of all kinds, over the years, CoreMark, looking at processor benchmarks. And then more specifically to the embedded space, we had EEMBC, that was headed up by one of our friends, Marcus Levy, for a while. And actually, they have a new president now. But the Embassy benchmarks, which measured power consumption and performance on microcontrollers and other embedded processors, was sort of a big deal for a while, but it kind of fell out of favor. Did you stop hearing as much, Rich, about Embassy, and why do you think so?
I've definitely stopped hearing a lot about Embassy. And to be honest, with all due respect to the Embassy folks, I don't think the engineering audience cares. It was a marketing thing. They would put the benchmark up there and people in the media like us bought into it, and it gave us something to write about. I don't think the engineers really cared.
Why is that?
Because they knew what they were getting. They read the data sheets. And, we just did some research on where you look for your answers for research for this kind of thing. And what came up over and over again was past experience. If I've used ST before, there's a really, really good chance I'm going to use ST again. And that goes for any of the vendors. Just because some benchmark says I'm going to get 8% better performance, it isn't worth me switching an architecture.
Well, nobody ever got fired for using IBM, right? If you've been using ST and you keep using ST, the boss isn't going to go, why the hell did you keep using ST, right?
Yeah. There's a lot more to it than that because of the code base, but yeah, that's definitely true.
So if you are entering now a new technology area, like let's say AI, where the code base potentially needs to be redone, or you're building it from maybe the ground up or close to the ground up, or at least extensions to your code base or branches. Does the viability of a benchmark come back into play because there's so many different? No, why not?
Nope. Because I am choosing my processor in an area like that where it's new and I'm not an expert. I'm doing air quotes again around expert. I'm going with the guy who's going to lead me further down the path. And some of these people like NXP are providing so much of the code to help me get there. Again, having that done for me is much more valuable than the 8-10% of the performance gain that you'll see in a benchmark.
Okay, but how do you know at this point? Isn't it a little bit early to be able to tell that NXP in fact is getting you that much further down the road with the code that they already provide in something like their EIQ, because you don't know where you're going to end up? Or
no, I don't think it's too early. I think it's mature enough that we're able to make that decision at this point.
So are you saying that you think a lot of the accelerators and stuff that are coming, you know, these DPUs and NPUs and all these things are just a little bit, so much more marketing?
No, I think they're very application specific.
Right.
You know, I mean, look at NVIDIA and the amount of code that they provide. They pretty much do the design for you.
Right.
You know, with the, you know, they have the GPU, you know, there's the TPU from Google. That's the way I would go. And if some benchmark said, if you switch to this thing that you might not have heard of, or you might have heard of, and you're going to get 10% higher performance, and my boss is saying, you know, this has to be done in 6 weeks. Yeah, I'm going with the guy who's going to help me get to the 6 weeks.
Yeah, for sure. I mean, there's certainly a lot of risk going into something that's application specific if you're on tight timelines and it's not proven, and you're not a huge company, you know, in which case you'd probably just be building an ASIC anyway, right? Well, all that being said, so apparently Rich won't be using this at all, but there's this new benchmark out that was developed by ML Commons in conjunction with MDC, called MLPerf Tiny, and this is MLPerf for inferencing. The MLPerf.
Are you a proponent of this? I mean, I'm talking about all the downsides. Let me hear why I'm wrong.
I was getting there. So I do think that I think it's valuable right now. I think it's valuable right now in the industry because there's still a cloud of confusion around machine learning and artificial intelligence. I do think that new branches of people's code bases are being written. And I think that it's valuable to start, it's a good opportunity, it's a good fork in the road to take a step back and say, you know what, is this architecture the architecture that we're going to be using to carry us forward? You know, maybe we've been using ST for the last 10 years, but you know, maybe the way that we're going to be developing our products, you know, in this vein or that vein, or this way or that way, is better suited to NXP, you know, over the next 5 to 10 years, if we're going to go really deeply into some, you know, computer vision enabled, you know, object, you know, product inspection on a factory line, or if we're going to be doing something really specifically related to voice, maybe we need to do something that's more suited towards, you know, Cadence Tensilica or hi-fi DSPs than whatever else we were using. And yeah, those are application specific, but I do think that right now it's a breaking point. You know, it's an inflection point, and more so than it was with IoT. You know, IoT was doing a lot of, let's just get really low power. Well, that was sort of, you know, we were always trying to get really low power, and let's add some connectivity to our SoCs. Well, yeah, but you know, things were trending that way anyway. Now we're talking about different types of compute that are fundamentally, change the way that you're processing a workload. If you're throwing in an accelerator that's kind of like a DSP and kind of like a GPU, but not really either of those things, that's going to have significant ramifications moving forward. And I understand that you don't want to do, for 8 to 10% performance, but some of these new architectures are claiming orders of magnitude, like multiple plural orders of magnitude more performance if you do it that way. And if that's the difference between doing edge AI on a battery powered device versus one that's not, I do think it's worth taking a look. And unfortunately, because the data sheets tell you, if it's sub-zero and, there's no wind and, all of these other things in the lab, you get this type of performance. There's no way for you to quickly evaluate apples to apples what you're going to get from an NVIDIA plus an NXP plus, or versus an NXP plus an S, or versus an ST versus a microchip versus on and on and on and on. So I do think it fills a gap. But the other thing that it does, this MLPerf Tiny Inference I'm talking about in particular, on the one hand, it's a negative because it's very open, it's very flexible. On the other hand, it's positive because the benchmark is architected such that you can evaluate, it's a full stack, and they have a reference benchmark that is, I think it in fact is an ST. But the full stack of the reference allows you to evaluate different parts of the bench of your system. So you could be looking at the AI framework that was used. Do you have a customized framework, or are you just using NVIDIA's TensorFlow, or compilers, or operating systems? So I do think that that's additional layers of benefit on top of just the hardware, the feeds and speeds, because really moving into the more system level benchmark, that's what the engineers at the end of the day care about. Really, how fast the processor runs or how efficiently it runs does have a big implication on your design, but we all care about what the system does, not what the components do.
In the time it took you to explain to me why I should look at the benchmark, I finished my design.
Next, Brandon and NVIDIA CEO Jensen Huang discuss the ongoing acquisition of ARM and NVIDIA's strategy amidst the global semiconductor shortage.
So Jensen, what can you tell us about the progression of the ARM deal, and also, if and when it's complete, where do you see value being generated for ARM, NVIDIA, and the end market?
Well, we're going through the regulatory approval, and it takes about 18 months. And the process typically goes U.S. Shortly engaged first, and then the EC, and then China last. That's the typical journey. And Mellanox took about 18 months or close. I expect this one to take about 18 months. So that makes it early next year, later this year, early next year. And so I'm confident about the transaction. The regulators are looking for, is this good for competition? Is it pro-competitive and brings innovation to the market? Does it give customers more choice? Does it give customers more offerings and more choice? And you could see that on first principles, because our companies are completely complementary. They build CPUs, we build GPUs and DPUs. They don't build GPUs really, not for deep, and they don't build TPUs. And so I think our companies are complementary, and so we'll bring, by nature, innovations that come as a result of companies that come together that offer complementary things. And so it's like ketchup and mustard, coming together. If we combine NVIDIA and ARM, ARM's R&D scale will be much larger. As you know, ARM is a big company. ARM's not a small company, but NVIDIA is much bigger. Our R&D budget is many, many times larger than ARM. And so our combination will give them more R&D scale. It would give them technology that they don't have the ability to build themselves, or the scale to build themselves, like all of the artificial intelligence expertise that we have. And so we can bring those capabilities through ARM to its market. And as a result of that, we will offer ARM customers more technology choice, better technology, more advanced technology. And that ultimately is great for competition because it allows ARM's licensees to create even better products, more vibrant products and better leading edge technology, which in the end market would give even the end market more choice. And so that's ultimately the fundamental reason of competition is customer choice. More vibrant innovation, more R&D scale, more R&D expertise brings customers more choice. So that I think is at the core of it. And for us, it brings to us a very large ecosystem of developers, which NVIDIA as a company, because we're an accelerated computing company, developers drive our business. And so with 15 million more developers, we have almost 3 million developers today, the 15 million developers would develop new software that ultimately would create value for our company. Our technology through their channel creates value for their company. And so the combination is really a win-win.
Obviously, even before talks of the acquisition of ARM, NVIDIA partnered with ARM using their technology, supporting their technology, but also Intel and x86 technology, as well as a variety of others. So if and when the ARM deal goes through, how is that going to change the way that you interact with other players in the market? And this Grace CPU could change things as well. So where and how do you see your relationship with these players changing moving forward?
I think the future world is very diversified. It will be x86, it will be ARM, it will be big CPU, small CPU, edge CPU, data center CPU, supercomputing CPU, lots and lots and lots of CPUs, enterprise computing CPU, lots and lots of CPUs. I think the world is very diversified. There is no one answer. Our strategy is we will continue to support the x86 CPUs in the markets that we serve. We don't serve every market, as you know. We serve high-performance computing, we serve artificial intelligence, we serve computer graphics. We serve the markets that we serve. And for the markets that we serve, not every CPU is perfect, but some CPUs are quite ideal. And so depending on the market and depending on the application and the computing requirements, we will use the right CPU. Sometimes the right CPU is Intel x86. For example, we have 140 laptops. The vast majority of them are Intel CPUs. We have our DGX system. We need a lot of PCI Express. It was really great to use the AMD CPU. In the case of 5G base stations, Marvell's CPUs are ideal, and they're based on ARM. Cloud hyperscale, Ampere Computing's Ultra CPU is really excellent. And Graviton 2 is excellent. It's fantastic. We support those. In Japan, Fujitsu's CPU is incredible for supercomputing. We'll support that. So different types of CPUs are designed for different applications. The CPU we designed has never been designed before. No CPU has ever been able to achieve the level of memory bandwidth and memory capacity that we have designed for. It is really designed for big data analytics. It's really designed for the state-of-the-art of artificial intelligence. And then meanwhile, there's so many different markets and edges and enterprise and this and that, and we'll support the CPUs that are out there. So I believe the future is really about diversity. I believe the future is about variability and customization and those kind of things. And so ARM is really a great strategy for us, and x86 will remain an excellent strategy for us.
I assume you're aware of the ongoing semiconductor shortage, and I'm pretty sure that you're aware of the rising price points of your products that are selling out almost as soon as they hit the shelves. In particular, I'm thinking about GeForce and Quadro RTX cards that apparently are being gobbled up by crypto miners. What are some of your plans to combat the volatility in supply and demand and then pricing that results from it? And how do you think the semiconductor industry in general is going to be able to deal with the shortage over the near, mid, and long term?
Yeah, our situation is very different than other people's situation, as you could imagine, because NVIDIA doesn't make commodity components. We're not in the DRAM business or the flash business or CPU business. Our products is not commodity oriented. It is very specific for specific applications. And in the case of GeForce, for example, we haven't raised our price. Our price is basically the same, and we have our MSRP. The channel end market price is a little higher because demand is so strong. And so our strategy is to alleviate, to reduce the hot demand that is caused by crypto mining, and create a special product, CMP, directly for the crypto miners. And if the crypto miners can buy directly from us a large volume of GPUs, and they don't yield a GeForce, and so they cannot be used for GeForce, but they could use for crypto mining, it would discourage them from buying from the open market. The second reason is we introduced new GeForce configurations that reduces the hash rate, the crypto mining rate. We reduce the performance of our GPU on purpose, so that if you would like to buy the GPU for gaming, you can. If you would like to buy a GPU for crypto mining, you could buy the CMP version, or if you really would like to use the GeForce to do it, unfortunately the performance is going to be lower. And this way it allows us to save our GPUs for the gamers, and hopefully as a result the pricing will slowly come down. In terms of supply, it is the case that the world's technology industry has reshaped itself. As you know, cloud computing is growing very, very fast. And in the cloud, the data centers are so big, like this. And so the chips can be very, very powerful. And so that's why die size, chip size continue to grow. And the amount of leading edge process it consumes is growing. Also, smartphones are using always state-of-the-art technology. And so the leading edge process consumption used to be some distribution, but now the distribution is heavily skewed towards the leading edge. Technology is moving faster and faster. And so I think that the shape of the semiconductor industry changed because of these dynamics. In our case, we have demand that exceeds our supply. That is for sure. However, as you saw from our last quarter's performance, we have enough supply to grow significantly year over year. We have enough supply to grow in Q2, as we guided, and we have enough supply to grow in second half. However, I do wish we had more supply. And so we have enough supply to grow and grow very nicely. And we're very thankful for all of our supply chain and all of our partners supporting us. But the world is going to be reshaped because of cloud computing, because of the way that computing is done.
So taking a tangent off that last question, GPUs, of course, they're big, but we also have seen the end of Moore's Law. What do these dynamics all mean for die sizes, transistor scaling, and process nodes of your NVIDIA solutions moving forward?
Since the beginning of time, the transistor time, die sizes have grown and grown and grown and grown and grown and grown and grown. And there's no question die sizes are increasing in size. And because technology cycles are increasing in pace, new products are being introduced every year, there's no time to cost reduce into smaller die size. And if you look at the trend, it is unquestionably to the upper right. And if you look at the application space that we serve, and I'm talking very specifically about us, if you look at our die size, there are always reticle limits now, and the reticle limits are pretty spectacular. I mean, we can't fit another transistor, and that's the reason why we have to use multi-chip packaging, of course, and we created NVLink to put a whole bunch of them together, and there's all kinds of strategies to increase the effective die size. Now, one of the important things, Tim, is that cloud data centers, so much of the computing experience you have on your phone is actually because of computers in the cloud. And the cloud is just, it's a lot bigger place. The data centers are larger, the electricity is more abundant, the cooling system is better, and so the die size could be very large. And so that's, I think die sizes will continue to grow, and even as transistors continue to shrink.
I'd be remiss if I didn't get a couple of your thoughts on the direction of the industry moving forward. Firstly, with regard to AI and how that's going to be impacting the development and deployment of technology as we know it. Then separately, more broadly speaking, what the direction of computing and electronics industries are.
As you know, artificial intelligence is software that can write software. And using machines, you could write software that no humans possibly can. It learns from an enormous amount of data using an algorithm, an approach called deep learning. Now, deep learning isn't just one algorithm. Deep learning is a whole bunch of algorithms, some for image recognition, some for recognizing 2D to 3D, some of it for recognizing sequences, some of it for reinforcement learning for robotics. There's a whole bunch of different algorithms that are associated with deep learning. But there's no question that we can now write software that we've not been able to write before. And so we can automate a whole bunch of things that we never thought were going to be possible in our generation. One of the most important things is natural language understanding. It is now so good that you could summarize an entire chapter of a book, or you could summarize a whole book. You could pretty soon summarize a movie. Watch the movie, listen to the words, and summarize it in a really wonderful way. You can have questions and answers with the natural language understanding model. And so AI has made tremendous breakthroughs, but has largely been used by the internet companies, the cloud service providers, and internet services. What we announced at GTC initially, and then what we announced at Computex, is a brand new platform that's called NVIDIA Certified AI for Enterprise. And these are NVIDIA certified systems running a software stack we call NVIDIA AI Enterprise. And the software stack makes it possible for you to achieve world-class capabilities in artificial intelligence with a bunch of tools and pre-trained AI models. A pre-trained AI model is kind of like a new college grad. You know, they got a bunch of education, they're pre-trained, but you still have to adapt them into your job, into your profession, into your industry. But they're pre-trained and really, really smart. They're smart at image recognition, or they're smart at language understanding, or so on and so forth. And so we have this NVIDIA AI Enterprise that sits on top of a body of work that we collaborated with VMware on, and that sits on top of NVIDIA certified servers from the world's leading computer makers. And these are high volume servers that incorporate our Ampere generation data center GPUs and our Mellanox Bluefield DPUs. And so this whole stack essentially give you a cloud native. It's like having an AI cloud, but it's in your company. And it comes with a bunch of tools and capabilities for you to be able to adapt it. Now, how would you use it? Healthcare would use it for image recognition for radiology, for example. Retail will use it for automatic checkout. Warehouses and logistics, moving of products and things like that. Tracking inventory automatically. And cities would use these to monitor traffic. Airports would use it to, in case somebody lost the baggage, it would instantly find it. So there are all kinds of different applications for AI in enterprises. And I expect enterprise AI, what some people call the industrial edge, will be the largest opportunity of all. And it'll be the largest AI opportunity. The computer industry is in the process of being completely reshaped. Artificial intelligence is one of the most powerful forces the computer industry had ever known. Imagine a computer that can write software by itself. What kind of software could it write? Accelerated computing is really the path that people have recognized is a wonderful path forward as Moore's Law or CPUs by itself has come to an end. I believe that the confluence, the convergence of cloud native computing, artificial intelligence, accelerated computing, and now finally the last piece of the puzzle, private 5G or industrial 5G, is going to make it possible for us to put computers everywhere. They'll be in far-flung places, broom closets and attics of retail stores, and they'll be everywhere and will be managed by one pane of glass. And that one pane of glass will orchestrate all of these computers while they process data and do artificial intelligence, process artificial intelligence applications and make the right decisions on the spot.
Now, Tiera Oliver explains how engineers from Knowles, Cadence, and ML Commons are working to advance the field of voice AI at the edge. If you've ever used a virtual assistant, you likely assumed you were talking to a device so smart it could answer almost any question you asked it. Well, actually, Amazon Echoes, Google Homes, and other devices like them usually have no idea what you're talking about. Yes, these devices leverage AI, but not in the way you'd expect. More often than not, the endpoint hardware simply detects a wake word or trigger phrase and opens a connection to the cloud where natural language processing engines analyze the request, and in many cases, they don't just transmit a recording of your question.
What was also beginning, what it started off with, we would call it like a really weak wake word at the edge, and then you would still have to send the entire recording up to the cloud to get a real solid second detect, that, oh yeah, someone actually said, okay, Google, or someone actually said the trigger word in question.
That was Vikram Srivastava, Senior Director of IoT Marketing at Knowles Intelligent Audio in Palo Alto, California.
And this would generate something that we call, true positive rate of detection, and something that we also call false accepts. So if you didn't say Alexa, but you sent a message to the cloud anyway, hey, I heard Alexa, and then the cloud will say, no, you didn't. I double checked and you're wrong. And that was more because the edge devices were not that sophisticated enough in their edge detection algorithms.
In other words, many virtual assistants go to the cloud at least twice. Once to verify that they're being addressed, and a second time to respond to the request. Not so smart, huh? There are several drawbacks to this architecture. Sending requests to the cloud adds time and cost, and also opens potentially sensitive data to security and privacy threats. But the most limiting factor of this approach is that opening and maintaining these network connections gobbles up energy, which prevents voice AI from being deployed in entire classes of battery-powered products. Here lies the challenge. Many edge devices use power-efficient technologies that don't equip the performance to run AI locally, and therefore must send voice commands to the cloud, which incurs the penalties mentioned previously. In an effort to escape this cycle, audio engineers at Knowles and elsewhere are integrating the traditional efficiency of digital signal processors, or DSPs, with emerging neural network algorithms to increase intelligence at the edge.
What we are seeing now is that the edge devices are beginning to transition to the built-in ecosystem. So now you can have up to 10, 20, 30 commands, which can be all executed at the edge itself. So some of just the trigger word improvements have happened significantly. And improve that the TPR at the edge. The other thing where audio DSPs actually played a big role, and audio algorithms at the edge play a big role, is just the performance of detecting these trigger words in noisy environments, right? So is my vacuum cleaner running and I'm trying to command something, or you're in the kitchen, your exhaust fan is running and you're trying to talk to your Alexa unit. So this is what we call low SNR, which means the noise environment you're in is very high, and our average talking.
Knowles is a fabless semiconductor company known for its high-end microphones and more recently for audio processing solutions. The latter began with Knowles' 2015 acquisition of Audience, a company founded on academic research in computational auditory scene analysis, or CASA, which studies how humans group and distinguish sounds that are mixed with other frequencies. That research led to specialized audio processors capable of extracting one clear voice signal from the background noise in the way Srivastava described. In addition to those audio processors, products like the Knowles AI Sonic Audio Edge processors integrate DSP IP cores from Cadence Design Systems. Cadence's Tensilica Hi-Fi portfolio of audio DSPs has gained popularity in intelligent edge voice applications thanks to its energy efficiency and an ability to efficiently digital front-end and neural network processing capabilities. Knowles deploys these Tensilica-based audio processing solutions into everything from single microphone AI Sonic smart mics to high-end devices like high-end Honeywell or Nest class thermostats, where they manage anywhere from 3 to 7 microphones.
Front end is all digital. So the microphones are digital, the DSP is digital, the communication between the DSP to the host processor is also digital. Suppose it is an Alexa device. So let's just say it's an Echo B device. So there's an ARM-based host processor in there that then is running what I would say, there's a little Alexa stack. That's what makes it possible. So we can take that 4 microphone data coming in, we can do beamforming, we can find out which direction you're talking in, we can improve and amplify your signal only from that direction, ignore the noise from other direction, and then do some other noise suppression as well. And then, detect, the trigger word accurately. In a well-tuned system, we would have less than 3 false detections in 24 hours. That's the accuracy we are looking for. And we can do that all within a 1 megabyte memory. And the value proposition behind having all of that in there is just to kind of give you an idea. If you needed like a ARM core running at 1 gigahertz to do speech processing, we would be running the same process at about 50 megahertz on our DSP. So almost a factor of 20 lower. So, and that directly translates into power consumption.
Obviously, Tensilica cores don't provide the same level of efficiency Srivastava is describing out of the box. Application engineers must tune the system for the end use case. For Cadence Tensilica customers, this process is simplified by the availability of custom instructions.
One of the things that's unique about Tensilica is its ability to use TIE or these instruction extensions.
Says Adam Abed, Director of Product Marketing at Cadence and a former Knowles employee.
Knowles uses that extensively to kind of really customize and build very efficient floating point processing. And so together we've kind of built this really nice unique product that's able to do not only deliver kind of high quality audio from the MEMS and microphone standpoint, but also be able to do some things like cleanup or voice trigger in a super low power manner without waking up most of the system.
To maximize both power efficiency and AI performance, the wake-up process Abed mentioned is usually implemented in phases depending on the system. As his colleague Yaipin Liu, Director of Product Engineering at Cadence, explains, IP like the Hi-Fi 5 requires.
So it's a combination of traditional DSP plus capability for process the neural network itself. And the first layer is to detect if there's actually any voice. So that's a very, very lightweight. Basically, is a voice activity detection. If it detects there is voice, then you wake up the next layer of processing. This is called what we call the keyword spotting or voice trigger. So that can be a pretty lightweight processing. it just says, I heard a word that sounds like what I'm listening to. It could take 50 megahertz.
Right.
So,
right.
Yeah.
Like everything, it depends.
Yeah, it really depends.
And when it comes to AI and ML technology evaluation, it really depends. Of course, determining how many megahertz, how much power consumption, keyword detection accuracy, and other key performance indicators of an intelligent audio system vary from design to design. Liu went on to explain that this variety makes it difficult to gauge the viability of smart voice system components, even DSPs, because metrics like the tera operations per second, or TOPS, don't actually matter when dealing with highly specialized DSPs.
If you can do 1,000 TOPS, but all the operations are the wrong type, it may need, it may need like 200 megahertz to process a certain type of processing. While if you have the right instructions, even though it's same number of TOPS, but it takes, for example, 50 megahertz instead of 200 megahertz. So essentially, you have more effective. Recently, though, ML Commons has looked to simplify the process of evaluating edge AI components by teaming with EEMBC on a new system-level benchmark, MLPerf Tiny Inference. As the latest in a series of training and inferencing benchmarks from ML Commons that span from cloud to edge, MLPerf Tiny Inference currently provides a standard framework and reference implementation for 4 use cases: keyword spotting, visual wake words, image classification, and anomaly detection. The MLPerf Tiny workloads are designed around a pre-trained 32-bit floating point reference model, which Kobe Branbury, PhD student in the Edge Computing Lab at Harvard University and MLPerf Tiny Inference Working Group co-chair, identifies as the current golden standard for accuracy. However, MLPerf Tiny Inference offers a quantized 8-bit integer model as well. What sets MLPerf Tiny apart as a system-level benchmark is its flexibility, which helps avoid single-point performance assessments of compute performance, for example, by allowing organizations to submit any component within an ML stack. This includes compilers, frameworks, or anything else. But being too flexible can be a negative when it comes to benchmarks, as you can very quickly end up with multiple vectors that aren't related. MLPerf Tiny addresses this through 2 different divisions, open and closed, which provide submitters and users with the ability to measure ML technologies for a specific purpose or against each other.
We have, MLPerf in general has this large set of rules. There's these 2 different divisions. There's the open and the closed division. And it sort of came out of this sort of constant pulling factor in benchmarks between like flexibility and comparability. And so the closed benchmark is something that's much more comparable. You take a pre-trained model and then you're allowed to implement it onto your hardware in a like equivalent manner that is equivalent to the reference model, based on some specific rules that have been outlined. And so that's really like a one-to-one comparison of hardware platforms. But the landscape of TinyML, it requires so much efficiency, and so many software vendors or even hardware vendors provide a value at all these different points in the stack. And so for people to be able to show that they have a better model design, or that they might be able to provide, better data augmentation or whatnot at the training phase or something, or even, different types of quantization and whatnot. That's where the open division allows you to essentially just, you are given the task, that is our use case. And you have to, solve it in whatever manner, whatever sort of target you want. And so we measure accuracy, latency, and energy, optionally energy. Okay. And so you're allowed to hit whatever optimization point.
In short, the closed division lets users evaluate ML components on specific characteristics, while the open division can be used to measure a portion or the entirety of your solution. In the open division, models, training scripts, datasets, and other parts of the reference implementation can be modified to fit the submission requirements. But back to voice, The ultimate goal of audio AI is the ability to perform full-blown natural language processing completely at the edge. Of course, this requires a lot more processing capability, a lot more memory, a lot more power, and a lot more cost than the market is ready for today.
And I would say we're still maybe 2 years away from true natural language at the end.
Says Knowles' Srivastava.
So having some of these local commands or the built-in capability, I think is the next thing. So that's where we are seeing our success right now is on low power battery based devices. I think that is still in a way in its early days because you need a lot of resources for natural language understanding at the edge. This is still the domain of the cloud. So over the last 5 years, we still haven't seen a lot of natural language come to the edge. But definitely we are getting subset of context specific commands moving towards the edge. And I think we'll see more and more of that as they fit in some of the embedded processors.
AI processing engines are being developed that promise to execute voice activation, recognition, and keyword spotting more efficiently, and enable more advanced natural language-based workloads at the edge. In fact, Knowles and Cadence are both actively developing such solutions. But in the short to midterm, there is still a need to make local decisions like voice trigger validation in real time while consuming less power. So with their legacy of efficient floating point processing on streaming data, why not try traditional DSP for novel new applications? And if you're not sure, there's a benchmark for that. Thanks for listening to this edition of Embedded Insiders. For daily news, videos, and podcasts, visit our website at embeddedcomputing.com.